So in this video, we're going to define the center of gravity for a rigid body. So, alright, and we're also going to define the center of mass, or the COM, or the centroid, which is also the center of volume for a rigid body. So our first definition, we're going to define the center of gravity for a rigid body. So if we have a rigid body, like we have drawn in figure 9.1a here. All right, this rigid body is of some arbitrary shape. Well, we can break this shape down into individual elements that are very small, and they have a very small weight, which we'll call dW. Okay, so what we're interested in finding is if we can determine using those small differential elements, can we use those to calculate the location of our center of gravity of our rigid body. So we would be able to calculate the total weight of our rigid body and where that total weight is being applied. So what that's called, so we'll say where that weight is being called, that is called our center of gravity, and its location in the XYZ coordinate system will be found using X bar, Y bar, and Z bar. Okay. So in order to determine that, the first thing we're going to do is we're going to sum all of our forces. All right, we're going to find our resultant force in the y direction. So we're going to sum, or in the z direction. So we're going to sum all of our individual elements to get our resultant force, which is just going to be equal to our weight. So our weight will just be equal to the integral of all those small differential elements. Okay. So what we're going to do now is we're going to take the moments about the different axes in our coordinate system. So we're going to sum all of our moments about the y-axis in our coordinate system. If we do that, that would be equivalent to taking the weight of our total rigid body and multiplying it by our center of gravity. And that would be equal to if you took the center of gravity of each element, which we'll define as x tilde, times the weight of each element. So if we integrate across our whole volume, it would be equal to the contribution of our total weight of our element times x bar. And we could do the same process for the x-axis. And if we do that, we can find come up with an equation for y bar using the centroid, or the center of gravity of our y component. And then if we go back and we look at figure C, if we rotated this whole coordinate system 90 degrees and the rigid body stayed in the same place relative to the coordinate system, so basically we have our gravity vector going down. In figure 1b, it's going along the z-axis, but now our gravity vector is aligned with the x-axis in this sense. So we're going to take the moment again about this axis and about the y-axis. And if we do that, we end up getting an equation for the z coordinate of our center of gravity of our rigid body. So for all three of these equations, we're going to divide on both sides by W. Right, if we do that, we end up with these three equations for the center of gravity, or the XYZ coordinates of our center of gravity for a rigid body. Okay, so again, the bars are the center, x bar, y bar, and z bar are the center of gravity coordinates for the entire rigid body, while x tilde, y tilde, and z tilde are the center of gravity coordinates of the differential element. So we can use our center of gravity definition to determine our center of mass of our object. So if we take equation 9.1, which was the equation on the last page, we have, if we look at equation 9.1, we can set the differential weight of our element as being equal to the uh, the gravitational constant times dm. And if we make that substitution into equation 9.1, we'll end up getting these three equations for the center of gravity of a rigid body. Okay, so x bar, y bar, and z bar in this case would not stand for the center of gravity, they would stand for the center of mass of our system. Okay, so we can do a similar substitution from our center of mass equation to calculate our center of volume equation. So in this case, we can set our differential mass element equal to rho times dv, okay, just using the definition of density, okay, and if we plug that in, all right, equation 9-2 becomes the following equation, where x bar, y bar, and z bar in this equation represent the center of volume of our rigid body instead of our center of mass or our center of gravity. All right. So the center of volume is typically the easiest, or is typically what you'll be asked to solve for the most during your homework problems and during exams, and it's probably the one that you most apply in practice. So the one thing I like to point out is that a lot of times, just by inspection of a rigid body, for in this case we have a cone here that its primary axis goes along the y-axis. So if you have if a rigid body is symmetric about an axis, or in this case two axes, its centroid must lie along that axis. Right. So in this case, we have symmetry about the z-axis and symmetry about the y-axis. So in this case, we know that x bar would be equal to 0 and z bar would be equal to 0 as well. Alright, so the only thing we don't know is what is y bar. So to calculate y bar, we would have to use this equation here. Alright, so in order to solve that, we need to determine what our total volume would be equal to. So the first thing we would need to do is define our differential volume element here, which we labeled as a small, we have it as a small disk. So the volume of a disk is equal to the area of the disk, which is equal to pi r squared, times its thickness, which in this case, it's going to choose a very small thickness dy. So we can set we can set we can say that r in this case is equal to z, so we can write this as being equal to pi z squared dy. Alright, and then if we integrate both sides, we could then solve for our total volume, which would be equal to, from y goes from 0 to the end of our cone, to, and then we substitute in our dv values here. So the only thing we need to do now is we would need to know what z is as a function. We had this find z as a function of y, and then we could plug that back in to this equation, and then we could integrate it, all right, to solve for our v. And then the only thing that you'd have to do to solve the top integral of that equation is you'd have to substitute in y tilde. And in this case, y tilde is just the centroid of our differential element, and y tilde in this case is just equal to y. Right? So you could do that integral as well, and if you did both of those, if you did those two integrals, you could find y bar, and you'd be able to solve for the centroid of the cone. So the centroid of an area is defined using x bar and y bar, so it's only 2D shape in this case. So you can solve for x bar and t bar using these two equations here. All right. So in both of these equations, you need to define three things. To solve both these two equations, you need to define three things. You need to determine what is x tilde, what is y tilde, and what is dA equal to. So you can do that using two, either a horizontal element or a vertical element. So we have a vertical element in the middle here, where our dA would be equal to the area of this small differential element. So that's equal to y times dx. All right, the centroid of our differential element, x tilde, is just equal to x, and y tilde is equal to y over 2. And then for our horizontal case, our area is here. Our differential area would be equal to x times dy. And then our y tilde would just be equal to y, and then our x tilde would just be equal to x over 2. Right? So depending on what is your function y as a function of x, you could use either of these elements to determine your x bar and your y bar. So you would pick the one that would be the easiest function to integrate in order to solve. So the last type of element that you would need to, or system that you would need to determine its centroid or its center of volume, would be the centroid of a line. So a center of a line is defined using this equation here. So in order to define the centroid of our line, we need to define three things: x tilde, y tilde, and the differential line element. So typically our x tilde and our y tilde will typically almost always equal, because the differential line element is such a small length. Our differential, our x tilde and our y tilde will just be equal to x and y. And then our DL element we can define either using these two equations here. Alright, so this should be, so I think this should be a y under here. Nope, never mind, sorry. That's correct. Alright, so so you can use either of these two definitions, and they get simplified down to these two. And then we end up getting, so you should choose the DL that makes your life easier. it results in a simpler integration. So in the case of this example here, we can define dl either as being equal to the square root of 1 plus the dy dx squared. So dy dx squared is equal to 4x squared, or 4x squared. Or you could define it as being equal to x is equal to y over 2 square root. So if you took the dx with respect to should be dx with respect to dy here, we would end up getting we'd end up getting 1 plus 1 half times 1 over 2 to the negative 1 half squared. Alright. So this equation is much easier to integrate. So we're going to use that differential element. So we can say that you would say dl would be equal to the square root of 1 plus 16x squared dx, and that would be plugged in to our equation 9.5, and we'd be able to solve for our differential, our centroid of our line. So the last thing I'd like to recap here is the general procedure of how you can solve these problems. So the first step for these center of gravity, center of volume, or center of mass problems is you need to define your differential element. So the first thing you'll do is you'll define your line element, your area element, or your volume, mass, or weight element, using the definitions that were discussed in the previous parts of the video. And then once you have those elements defined, you need to define those three elements in terms of the coordinates or the functions of the curve or the rigid body that you're solving for. So you basically need to put everything in terms of a single variable so you can solve it. And then using those, you need to also determine the x bar, y bar, and z bar, the centroids of each of the elements, or the center of gravity for each of the elements within the total volume, using your differential element. And once you have those defined, you just need to plug them into your equations and integrate. Okay, so after you get through your definitions, all you have left is just to integrate, and you'll end up with your final solution. Alright, so that concludes this video on center of gravity, center of mass, and center of volume of continuous rigid bodies.